Good afternoon and welcome to our lesson. We are still on images and how they are formed by curved surfaces. Right now we want to look at the mirror formula and see how we can describe the position, the size, as well as the focal length of a concave reflector. Now, the mirror formula is basically the relationship that exists. It is the relationship that exists between U, V, and F. The relationship that exists between U, V, and F, and where U is the object distance, V is the image distance, and then F is the focal length. Focal length of a curved surface. The focal length is actually the distance. Is the distance from F to P. Now remember, we looked at some parts of a reflector where we said we could call this C, this is F, and this one is the pole. Now the distance from F to where the pole is, this one here, this one is what we call the focal length. The focal length. Now, as we move on, we are going to realize that we actually have a relationship that exists among the three, and which helps us to calculate any one of them should we be required to do so. Now, we are going to start by stating the formula itself. And the formula states that 1 over F is equal to 1 over U plus 1 over V. That is the relationship that exists between the three, and it is a very important relationship in the study of curved surfaces, as it will enable us to calculate different aspects of the curved reflectors. Now, from this formula, we can decide to add the right hand side we can add the right hand side so that 1 over U plus 1 over V, we add the 2, get the LCM, will be UV, then we can divide so that now that one is the sum of the two. But remember, the right hand side is not, the left hand side is not changing, so 1 over F can be equated to that, so that we have V plus U over UV, something like that. Then we can get the reciprocal of this, so that now F becomes UV over U plus V. So from the mirror formula, we can also be able to come up with a relationship between U and V, which we can use to get f, just like any other quantity that we could be interested in. Now, before we go to the calculations, I want us to look at some graphical analysis of the mirror formula. Graphical analysis of the mirror formula. And we shall draw a few graphs. For example, let us draw a graph of 1 over v against 1 over u. A graph of 1 over v against 1 over u, so that we plot 1 over u, so that we can against 1 over u, so that on the y-axis we have 1 over v, on the x-axis we have 1 over u. This graph is going to be a straight line. With a negative gradient. It's actually a straight line with a negative gradient. And a negative gradient in this case implies that the object, not the object but the image, implies that the image is actually inverted. The image is inverted. That a graph of 1 over v against 1 over u is a straight line, but it has a negative gradient, and this one should imply that the image that is formed is actually inverted. Now, something else you are going to note that the y and x intercepts, if you are accurate in the plotting of your graph, you will realize that y and x intercepts of this particular graph are actually equal. And they give the value of 1 over f. That the gradient is negative, implying that our image is actually inverted. Then we have intercepts which are equal, and that one should imply that the value of the intercepts is actually 1 over f. Now, we could also talk about another graph. UV against U plus V. A graph of UV against U plus V. Again, we sketch this graph. On this axis we plot UV. On the x-axis we plot U plus V. Now this graph is going to give us a straight line which is actually through the origin, and the gradient which is given by change in y over change in x is going to be given by change in UV over change in U plus V, which gives us the focal length. This one is actually the focal length. It gives a straight line through the origin, and the gradient is the focal length. The gradient is actually the focal length. Now, look at this. 1 over F will be equal to 1 over U plus 1 over V. Let us multiply. Let us multiply by V throughout. We have our mirror formula. Now we want to multiply all through by V and see what we can get from that. Now, if we multiply by V, V over F will be equal to V over U plus V over V. Now, this one is linear magnification. Or what we call small m. Then this one gives us 1. Therefore, our equation can now be V over F is equal to magnification plus 1. Magnification plus 1. That we took the mirror formula, multiplied all through by V, so that on the left hand side we have our image distance divided by the focal length. On the other side we have V over U, that is image distance divided by the object distance, and that one should give us linear magnification. And then we have a whole number fraction of 1. Therefore, V over F is equal to magnification plus 1. Now we want to make M the subject. Making M the subject of the formula, we subtract 1 both sides, so that now we shall have V over F minus 1. So from the mirror formula, we again can come up with an expression of magnification, which is given by V over F minus 1. V over F minus 1. Now, the last graph that I want us to look at is that one M against V. M against V. And again we will get a straight line. So this time we are going to have a y-intercept, not really through the origin, but rather we are going to have a y-intercept. And an x-intercept. Now, y-intercept will be equal to -1. Remember, we have plotted m against v. We are going to have a straight line, and that straight line graph is going to have an intercept, a y-intercept equal to -1, and the gradient is a straight line with its y-intercept equal to -1. Now, something else that we will note about this graph is that the gradient is equal to 1 over fork length. The gradient of this graph is equal to the reciprocal of the fork length. The reciprocal of the fork length. Now we can look at some applications. We can look at some applications of the mirror formula, which we have just looked at. 1 over f being equal to 1 over u plus 1 over v. And we said that this is actually a very important formula in the calculation of any of the three quantities in the relationship. Now we shall look at something we call sign convention. Sign convention. Now there are some rules that govern the application of this formula. For example, number 1 is that all distances are measured from the mirror. They are actually measured from the mirror. That is rule number 1. Then we have number 2, that real distances are considered. They are considered positive, while virtual distances are considered negative. Now, this is what we mean. If we were to look at a concave reflector, for example, here we have our F, we have our C. Now, this distance from the pole has to be measured from the reflecting surface. If we want the radius of curvature, we have to measure it from the reflecting surface. So that now, if we talk about our C being equal to 30 centimeters, it means that it's 30 centimeters from the mirror to the center of curvature of the reflecting surface. Every distance has to be measured from the reflecting surface. Now, in the course of drawing our ray diagrams, we discovered that there are some images that are going to be virtual. Virtual images mean that their distances from the mirror is not real. Now, it means that distance from the mirror is virtual. For example, we looked at the case of a convex reflector, and we found out that if this was to be F, this was to be C, we found that the object will always be formed, the image will always be formed between F and P. And in this case, rays do not pass through these points. The rays actually appear to pass through the points. And for that reason, we classified these images as virtual. Now, it means that the distance from the pole to where the image is located is also virtual. And if the distances are virtual, even the height is also virtual, because the image as a whole is not real. The image as a whole is not real. The image is not real. Therefore, when we are dealing with our mirror formula, we shall take note of that, and we shall treat the distances as negatives. For example, we have examples. If an object is placed if an object is placed 30 centimeters from a concave reflector whose F is 20 centimeters, we are supposed to calculate the image position. That we have a concave reflector whose focal length is 20 centimeters, and we place an object 30 centimeters away from the mirror, then we are supposed to get the image position or the image distance from the mirror. Now, in our solution, we ask ourselves, this is a concave reflector, and we have our object placed between F and C, because if this one was to be 20, then 30 is somewhere there. Therefore, the object is actually between F and C. Now, for a concave reflector, images formed are real amongst other characteristics. We were able to establish that actually these mirrors form real images, apart from a situation where you've placed your object between F and the pole. All the other situations formed a real image. Now, why am I taking trouble to explain to us? It is because we have been given F as 20 centimeters. And then we have the object distance, U, as 30 centimeters. Now, before we even proceed, we should ask ourselves, are these distances real or virtual? Now, it's a concave reflector, which qualifies the F to be positive. Then, the distance of the object will always be positive because the object must be there. It has to be a real object, which means it has to be placed a real distance from the mirror. And for that reason, even U becomes positive. Now, from our mirror formula, 1 over F is equal to 1 over U plus 1 over V. Now, what we do not have and what we want to look for is V. Therefore, it's only fair to make 1 over V the subject of the formula, so that now 1 over F will be minus 1 over U will now give us 1 over V. Will give us 1 over V. Now let us substitute then. If 1 over F minus 1 over U is equal to 1 over V, then we can substitute in the formula so that 1 over 20 minus 1 over 30 becomes 1 over V. Now, we have put in the values that we have so that they can enable us to work out what we do not have from the formula. Now, let us get the LCM. The LCM of 20 and 30 is actually 60. Then 60 divided by 20 multiplied by 1 gives us 3. 60 divided by 30, and then we multiply by 1 gives us 2. Therefore, one over V will be equal to 1 over 60. Now, if 1 over V is 1 over 60, then V becomes the reciprocal, which is going to be 60 centimeter. In this case, positive 60 centimeters. Positive 60 centimeters. Now, we have now found that 1 over F is 20, we have found out that F is 20 centimeters, U is 30 centimeters, and V is 60 centimeters. with the help of our mirror formula. Now what remains is part 2 of the question, which requires us to get linear magnification. Linear magnification. And in our previous lesson, we were able to establish that linear magnification is actually given by object, not object, but image. Image height over object height. And this one is also equal to image distance over object distance. Image distance over object distance, and it's also a ratio of the heights. Now, in our case, we have also found from the mirror formula that magnification can also be V over we have also found out from our formula that magnification can also be given by V over F minus 1. Now, in this case, we have the distances, and we have, so we can find out, can this one give us the same result as this one? Because we have the distances, and we even have the fork length, so we can compare the two. Number one, we have image distance, which is V over object distance, which is U, and V in our case is 60 centimeters. You divide by U, which is 30 centimeters. Now, let us cancel where possible, so that now we have our magnification as 2. Now that is the first method, that we have taken the image distance, we have divided by the object distance, so that magnification now becomes 2. Now the alternative that we have is to take V over F, then we subtract 1. Now in our case, V is 60, F, these are centimeters, F is 20 centimeters, then the whole of this minus 1, so that in our case we have by 21 by 23, we have from the brackets 3 and we subtract 1, so that we have a magnification of 2. So either method can give you the same result. Now that brings us to the 5th aspect of the images that we have. When you draw the image to scale, you give the 4 characteristics that we give. That's the nature, the posture, the position, and the size. And you can also include linear magnification. You can also include linear magnification. Can include linear magnification. we would like to look at yet another example. And we call it example 2. That will require us to determine the position and magnification in the following cases. Number 1, object placed. An object placed 18 centimeters in front of a concave mirror whose F is 12 centimeters. Now, that one is the first case. We solve it, then we can have the second case. In this case, we are supposed to get the position and magnification of an object which is placed 18 centimeters in front of a concave reflector whose fork length is 12 centimeters. Now, to our solution, ask yourself, what does the question provide? Like in our case here, we have a concave mirror, which means that F is very positive, 12 centimeters. Then we have another one, which is U, and it is 18 centimeters. The object distance is always real. And in our case here, we have been given an object distance, which is 18 centimeters. Now, let us apply the mirror formula. Let us apply the Miller formula, which is 1 over F gives us 1 over U plus 1 over V. That is the Miller formula. And we can substitute. But first, we make 1 over V the subject of the formula, so that now 1 over V will be 1 over F minus 1 over U. Now, evaluating by way of substituting where possible. We find out that 1 over V is going to be given by 1 over 12 centimeters minus 1 over 18 centimeters. 1 over 12 minus 1 over 18. and we get the LCM. In our case here, the LCM is going to be 36. 36 we divide by 12, which becomes 3. Multiply by 1, 3 remains. 36 divide by 18 will give us 2. 2 multiplied by 1 gives us a 2 again, implying that 1 over V is going to be given by 1 over 36. But the question does not require us to get 1 over V. Rather, we are required to get V in itself. So we get the reciprocal. No. We get the reciprocal. Both sides, so that now V over 1 becomes 36 over 1, implying that V is equal to 36 centimeters. V is 36 centimeters. So for our first case, we have U being equal to 18 centimeters, V being equal to 36 centimeters, and F being equal to 12 centimeters. Now we go to the second part of the question, which is to get the magnification. Now, in this case, we are going to use our two methods and find out whether they yield the same results. Method 1 is where we compare image distance to the object distance. Now, that is the first. With what we have, we can substitute so that now we can find out whether the two will give us the same result. Now, the method number 1 on how to go about getting magnification is where we compare the distances. In this case, V over U. Our V was found to be 36 centimeters, and our U is 18 centimeters. 18 centimeters. So we can go ahead and cancel where possible. So that now we go by 9, 2 by 9, 4. Then we can cancel by 2, 1 by 2, 2. So that our magnification becomes 2. Now, what does magnification of 2 mean? It means that if you compare the size of the object and that of the image, you find that the size of the image is actually twice that of the object, that the image is twice as big as the object. Now, we want to consider method 2, where we said that magnification is given by V over F minus 1. Find out. We still have the same distances. Nothing has changed, only the formula. So, if 2 be our magnification, whatever formula we apply, we are supposed to get the same result. So let us then substitute so that now V is 36 centimeters, F is 12 centimeters, and then the whole of that minus 1. Cancel by 12, by 12, 1, by 12, 3, so that this one will give us 3 minus 1, and we are back to our 2 as linear magnification. We have 2 as our linear magnification. Now, we had another case, case 2 of the same question. Case 2 now is an object placed 6 centimeters in front of a concave mirror of focal length (12 centimeters). That is our second case. We have now the focal length being 12, but this time the object distance has now changed from 18 centimeters to 6 centimeters. Now, I'm imagining that we are plotting this case, so that now that's the pole, that's F, and that's C. Our focal length is 12 centimeters. Our focal length is 12 centimeters. Our focal length is 12 centimeters, this one here. Now, our object distance is somewhere here. That is where our object is, so that if we measure again from the mirror to where our object is, we have a distance of around 6 centimeters. We have a distance of around 6 centimeters. Now, if we go back to the ray diagrams that we drew, now we consider a ray like that is supposed to be reflected through F, then we have another one through F. If we had our object between F and the pole, object between F and the pole, object between F and the pole, it is supposed to be virtual, upright, and enlarged. It's supposed to be, the image is supposed to be upright, enlarged, and virtual. Let us try and come up with that kind of a sketch. Let us try and come up with that kind of a sketch where we have F here, we have C, then we place our object somewhere there so that we can consider a ray which is parallel to the principal axis and is going to be reflected through F, Then we can consider a ray through C. We can consider a ray through C, and this ray, we expect it to pass on undeviated. Now here we are going to form an image. We are going to form an image that is actually erect. It's bigger than our object and in the opposite side. Now what should that tell you? That one should tell you that should you resolve the distances and find out that V is actually positive, then there is something wrong with your calculations. There is something wrong with your calculations because we say that virtual distances will always be negative. Now, to the working, and we are going to consider F being equal to 12 centimeters, U is 6 centimeters, and V is what we want to look for. But we have our formula. We have our formula as 1 over F equal to 1 over U plus 1 over V. Now, let us work out the value of 1 over F. Again, 1 over V, work out the value of 1 over V by making it the subject of the formula. And let us now try and substitute for F and U in our new found formula so that 1 over V is equal to 1 over 12 minus 1 over 6. 1 over 12 minus 1 over 6, get the LCM, which is going to be 12. 12 divided by 12 is 1, multiplied by 1 gives us 1. Therefore, that will be 1. Take your 12 again, divide by 6 gives you 2. 2 multiplied by 1 is again 2. So subtract 2. So that now your value of 1 over V is going to be negative 1 over 12. Negative 1 over 12. Therefore, try and get V. If 1 over V is 1 over 12, it implies that V is now equal to negative 12 over 1. That is the reciprocal, which is going to give us negative 12. Now, from what we know about the sign convention, we have been able to affirm that where we have virtual images, the distance are going to be negative. So, now let us try and get the magnification. Now remember, now we have F being equal to 12 centimeters, U being equal to 6 centimeters, and V being equal to negative 12 centimeters. Now we want to try and come up with linear magnification, and we again use our first method. We use our first method where magnification is V, the ratio of the distances, and this will give us negative 12 centimeters, and we divide by 6 centimeters. Again, our magnification becomes negative 2. Why negative 2? We have used the same reflector. Why negative 2? Much as the magnification of the concave reflector is 2, this time the image that was formed was virtual, as opposed to the other two cases that we have looked at. This time round the image was virtual, and therefore the sign should only be there to confirm that your image is not real. Now, let us confirm our answer using our second method. Let us confirm using our second method, where magnification is V over F minus 1. V over F minus 1. And V is negative 12 centimeters. F is 12 centimeters. Then the whole of this minus 1. The whole of that one minus 1. And you can cancel where possible. Do away with the units, because magnification is a ratio of distances. You do not expect it to have units. Then by 12, 1 by 12, 1. This leaves you with negative 1. Subtract 1 will give you negative 2. So whichever method you choose, it's actually supposed to yield the same result. But now, why should we say that magnification does not have units? Magnification does not have units because it is a comparison between distances or sizes of objects. Now, if you choose to use the 3, probably we can note why magnification does not have units. We can note why magnification does not have units. And we are going to look at the three methods of getting magnification. Number 1 is image height. Image height over object height. Now, look at this. That magnification is the ratio between the image height and the object height. Both of them are heights. They are heights. That means that the first step when you are looking for magnification using that formula is to cancel out the distances, is to cancel out the units, because we have height and we have height. Therefore, the units will be similar. You can cancel them before you even proceed. Number 2, we have image distance over object distance, giving us magnification. Again, you look at this formula, you have distance as your numerator, you are comparing it to another distance, which is your denominator. That means the units will be similar. You will cancel them before you move ahead. The third and last formula is where we have V over F minus 1. V over F minus 1, giving us magnification. Again, V is a distance. F is also a distance. So you can cancel the units, and that is why magnification does not have units. So we say it is a comparison between similar quantities. It is a comparison between similar quantities, and for that reason we say it does not have units. It doesn't have units because it's a comparison between similar quantities. Now, I look at the relationship between F and C. Now, in our ray diagrams, we've kept on looking at 2 very important points of reference, where we have had F, then we have had C. F and we have had C. Then here we can put our pole and probably assume that that one is our reflecting surface. Now, one thing you should know is that C is actually the center of curvature, or the center of the sphere of which the mirror is part. Now, the relationship between this distance here and this one here is what we are actually interested in. This one, we call it, let me give it X, and this one I call it D. Now, X is the focal length, and conventionally it is represented or denoted using F. Again, we have D, which is the radius of curvature, and conventionally it is denoted using small r. Therefore, we can now delete our letters and put the conventional ones, where now we will put F there and R there. Now, we said that distances should always be determined from the reflecting surface to wherever it is that you want to measure. Now, the relationship that exists between the two is that F is equal to a half R. F is equal to R over 2, or R is equal to twice F. That is the relationship that exists between the two. So should anybody require you to get any one of them, for example, a question of this nature, you can get a question of this nature: calculate the radius of a concave mirror whose fork length is 15 centimeters. That you calculate the radius or the position of C of a mirror whose fork length is 15 centimeters. Now, when you get such kind of a question, you should not panic. You just apply the relationship F is equal to R over 2, implying in our case that 15 centimeters will be equal to R over 2. And for your R, you can multiply all through by 2, so that R becomes 2 multiplied by 15, giving you 30 centimeters, giving you 30 centimeters, giving you 30 centimeters. Now, I want us to look at the very last aspect of mirrors, which is the application bit. Now we have the knowledge of concave and convex reflectors and how they form their images, the characteristics, how to describe the image, and so on and so forth. So the most crucial question that we ought to ask ourselves then, how should the reflectors be of help to us, or how can we apply them in our daily activities? We start by looking at we started by looking at types, and we said we could have 3 types, where we have concave reflectors, we have convex reflectors, and we have parabolic mirrors. Now, I will start by concave reflectors, and we list down the applications. Applications of concave reflectors. And number 1, they are used as shaving mirrors. Number 1, they are used as shaving mirrors. Number 2, they are used by dentists to examine teeth. Number 3, as reflectors for projection lamps. For projection lamps, you could also use them to make reflecting telescopes. And lastly, you can use them as solar concentrators. You use them as solar concentrators. So they have basically those 5 applications. You could use them as shaving mirrors. You could use them to examine your teeth, to make the reflectors of for projection lamps. You can make telescopes or even solar concentrators. Solar concentrators. Then we have convex reflectors. Are they of any help to us by any chance? Now they are used as driving mirrors. You could use them as driving mirrors, or you could use them in supermarkets. To monitor customers. You could use them in supermarkets, so you could monitor your customers. Now, parabolic reflectors. Parabolic reflectors, they are used as headlights, car headlights. They are used as car headlights, or you could use them as spot lights. So each one of these reflectors is important in its own way, in that we can apply them in our daily activities to do things that are very basic in our lives. That's about all to do with mirrors. Next time we meet, we will look at waves. And how we can also manage to use energy emanating from waves. Thank you.